Before I begin today's lesson, just based on yesterday, right? We learned antiderivatives. If I started by handing you this, what would you guess the antiderivative or the indefinite integral would be? So let's just guess. Could it possibly be that the answer is negative cosine of 3x plus 8 plus c? Would this be correct? Well, we know, and we discussed yesterday, how to check. So let's check. Well, let's differentiate this. We get derivative of cosine is negative sign. With this negative, we will have a positive sign. But then, really, this is a chain rule. So times 3. And then derivative constant is 0. This is not correct. This is not equal to sine of 3x plus 8. Okay, so this is not the answer. And we see that by checking. Now, what is the answer? Well, the answer is negative 1/3 cosine 3x plus 8 plus c. And why? Let's check. Okay, if I differentiate this function, okay, this is chain rule. We would get positive 1/3 sine 3x plus 8 times derivative of the inside function. The 3 times 1/3 is 1, and so we get sine 3x plus 8. And so just by sort of guessing and checking, we see the answer here. Maybe I'll even write it above. This is negative 1/3 cosine 3x plus 8 plus c. And we got that sort of by guessing and checking, but the technique we will learn today, we will be able to address this in a systematic way to find this. And maybe after you watch the video, or after you watch even the first 15 minutes of the video, come back and see if you can work this problem using substitution. And if you do it correctly, you will get exactly this as the antiderivative. Today's lesson is a really important day. It's called substitution, and this is a technique for integration, and quite an important one that we see all the time, not only this semester, but also Calculus 2. Before we begin, let me talk about something from derivatives, which is the chain rule. If you differentiate a composition, well, we get the derivative of the outside, evaluate at the inside, times derivative of the inside function. And substitution is the corresponding integration technique. So substitution, I'll put this sort of in quotes, this undoes the chain rule. And what do I mean by this? Well, if I integrate this part, this is the derivative. So if I integrate f prime of g of x times g prime of x dx, I will get this f of g of x and then plus c, okay? So this, which is saying something about an indefinite integral, is the same thing as this chain rule that we have been working with for a while now. Now, how do we proceed with a problem that's integration by substitution? Well, just like when we started chain rule, the very first thing we want to do is look for an inside function, and that's the first step here. Except, sort of looking at this integrand, we will not typically have just an inside and an outside function. We will have here inside function, and you see what else I see? I see its derivative in the integrand, and this is something that is important with substitution. So how do we find a problem by substitution? Step 1, we look for an inside function. And typically we will refer to this as u. Oh, I'll write it over here. Then, what are the following steps? So I think of substitution as being 5 steps. Here's number 1. And maybe as I write the remaining 4 here, we can work through a problem as we do. So here, now we see the first indefinite integral we will calculate using substitution. And let's go ahead and do this first step. Look for an inside function. Well, we see here 3x squared minus 5 is inside parentheses. And so step number 1, I will write u as what's inside the parentheses. Now I typically won't number all 5 steps once I practice more, but for the first few, I will. Well, what comes next? What we want to do is calculate du. What is du? Let me write it here. Du, maybe I will put this part in purple. It is du dx times dx. Now it looks like I might have not written anything because it looks like the dx's cancel, but this is not the case. This says du. This in purple is the derivative, and then times dx. So now let's do step 2 here in this problem, du. Look at this function and take the derivative. It's 6x and then times dx. Okay, there's step 1, there's step 2. Now step 3, generally, we want to convert the entire integral to an integral of u. You might remember, hopefully you remember from last time, every integral has an integral sign and then a d, whatever your variable is, ends it. So when I convert this blue integral to an integral of u, every single piece gets substituted with something of u, and this is I think about the substitution name coming from. So this piece must be something of u, and this piece must be something of u. You do not want to mix u's and x's in the same integral. Okay. Well, if we look at this, maybe I will add purple here. This part, look, we've calculated it. This part is du. And then here, inside the parentheses is u. And so you can kind of see we have u to the 7th du. So here, step 3, my integral is an integral. It's u to the 7 du. Now, step 4, we integrate. And this is integration with respect to u. Integrate with respect to u. If you look at this in black, this is something I can integrate. It's a very simple power rule. So here is step 4. This would be u to the 8 over 8 plus c. Now we're not finished. Don't just integrate with respect to u and be done, because I started off with a function of x and I need to give an antiderivative that is with respect to x. And so step 5 is we go back to x, or whatever your original variable happens to be. In this case, it's x. Step 5, oh, let me underline. Step 5 is function composition. Okay, so here, step 5, which will be our final answer, we know, looking here, u is 3x squared minus 5, and so I put that in here. So I get 3x squared minus 5 to the 8 over 8 plus c. And now this is our final answer. We have integrated. Okay, here. So this is the final answer. And if you want to check your work, this is something you could do, right? This is chain rule. Just differentiate this function. You will get exactly here, 3x squared minus 5 to the 7th power times 6x. Okay? These are the 5 steps of substitution. And let's do some more examples. Let's look at this example, our second one. And for the moment, I have left these 5 steps of substitution on the board. If you look at this, you may not see clearly an inside function. It more looks like a quotient, but we don't really learn a corresponding integration rule for the quotient rule. And here we can use substitution. One place you might remember you can look for an inside function is in the denominator. And this is what we will do here. So if u is x cubed minus 4x, there's step 1. Step 2, du. We take the derivative, 3x squared minus 4, and then times dx. Now, one thing that you can do, especially when you're first starting substitution problems, is you can rewrite the integral so that everything involving u is grouped, and then everything that didn't have a u, you can group with the dx. Okay, so here this part is grouped. And you see these two are exactly the same. I've just moved how I wrote the integrand. But now you see, handed to me in my integral is exactly du, and then this is a 1 over u. So when I move to step 3, my integral with respect to u is 1 over u du. Step 4. Well, we know an antiderivative here. It's ln, absolute value of u, plus c. And then the final step here, composition. We go back to the original variable x. We get ln, absolute value, x cubed minus 4x plus c. And this is our antiderivative here. And yet again, if you would like, you can differentiate and check, and you will get exactly this integrand. This might be the last one where I number the steps, and then I will show you how I normally show my work. But here we go, 5 steps. They're erased, but we will talk through them. Here, up inside the exponent of e is, without a doubt, an inside function. So step 1, u is t squared minus 2t. We find du, 2t minus 2 dt. Now, again, just like the last example, I could rewrite this integral to where I group this. And then this part, the t minus 1, I move and group it with the dt. So this part is grouped. Now, this one is different than the first two we have seen, because if you look at this, t minus 1 dt, and then you look at this, it's not the same. So we do not have exactly du handed to us in our integral. And this type of example takes a little bit, well, one more step, I will say. So what I typically do, you see, it's grouped. And then I write what we have. We have, instead of having 2t minus 2, we have t minus 1 dt. And this will be some multiple of du. Okay? Well, we see, to go from this line to this line, we're just dividing by 2, or you could factor out a 2 from this line and divide. So the multiplier here is 1/2. And you can check, multiply this line by 1/2. You get exactly this on this side. Okay, so what that means when we move into step 3, this part is 1/2 du. And this is an important part of substitution, is getting this multiplier correct. Let's move into step 3. We have an integral. It's e to the u times 1/2 du. Now we integrate with respect to u. This would be step 4. Well, the integral of e to the u, this is e to the u. We have 1/2 times e to the u, so we integrate, we get 1/2 times e to the u plus c. And the final step, we go back to the original variable, which is t in this case. We get 1/2 e to the t squared minus 2t plus c. And this is our final answer. These next 2 examples are ones that I had on the board at the end of the last video when we had our discussion about antiderivatives. And I mentioned in that discussion that we would do both of these today using substitution. So perhaps we will begin with the one on the left. We see parentheses. So we see the inside function, it's x to the 4th minus 1. U is x to the 4th minus 1 du for x cubed dx. Now, you see, what do we have handed to us in our integral? And you could rewrite this to group the x cubed with the dx, but we have x cubed dx. Okay, so we have x cubed dx. And this is 1/4 du. So typically, I will put this much in a box and then continue the integral. So this integral it's an integral of u to the 3/2 times 1/4 du. And then we integrate, we get 1/4, we add a power, divide by the higher power, plus c. Before I go back to x, let me just fix this. When we invert and multiply 1/10, u to the 5/2 plus c. Now the final step is go back to x. So we have 1/10, x to the 4th minus 1 to the 5/2 power plus c. Okay, this was substitution. Now let's move to this example. This is one where it may look like you're not sure what to do, but in my denominator, I have e to the x plus 8, and the derivative of e to the x plus 8 is e to the x. So I have a function in my denominator, and I have its derivative in the integrand. So this suggests my u should be e to the x plus 8, and du is e to the x dx, and we have exactly e to the x dx. Okay? Then, when I convert, I get an integral. This is 1/u du, which we have integrated this one already today. It's ln, absolute value of u. And then the final step, we have ln, absolute value, e to the x plus 8 plus c. Now, you could change the absolute value to parentheses because e to the x plus 8 is always positive. So you could do this if you wanted. But you cannot break this apart. There's no log property for when you have a sum on the inside. So here, this is our final answer, or you could leave it with the absolute values. Here are 2 more great examples. Here, in the denominator we have a radical, and so it's very natural that the function underneath the radical is our choice of u. Okay, here we have u is 3t plus 2 du. Well, it's 3 dt. Okay, we have minus 3 dt, and this is negative 1 du. Okay, so then this integral becomes an integral. I'll write it this way, u to the minus 1/2 times minus 1 du. Okay, now we integrate. We have the negative sign from here, and then we add a power, divide by the higher power, plus c. This is minus 2 square root u plus c, and the final step, we go back to t. So we have minus 2 square root 3t plus 2, and then plus c. Now, every single step I have written is important in showing your work. You must write what is u, calculate du, and don't forget that this includes the dt here. du is not 3, du is 3 dt. And then you should show an integral entirely of u. And like I said, you do not want to mix u's and t's in one integral. That doesn't make sense. So you can write an integral entirely of t. This is fine. You can write an integral entirely of u. This is fine. Okay. Then we integrate with respect to u and then go back to our original variable. All 5 steps are part of integration by substitution and should be a part of your work. Now, let's do the one on the right. You might look at this and see, wait a second, I don't see an inside function. Okay, I have a quotient, but what's in the denominator wouldn't make sense for a u, like in the examples we've seen before. But we have to think a little bit sometimes about what would be the best choice of u. Here, we see an ln x, and the derivative of ln x is 1 over x. So in fact, if we take u to be ln x, du is 1 over x dx. And you see, we do have 1 over x dx in our integral. So this is a very great choice for substitution. Then the integral is simply u du. And now we integrate. This is u squared over 2 plus c, and then we go back to the original variable, which is ln x. And this would be our final answer. These next 2 examples are kind of similar in that they're sort of a single function. So we have a to the x, and we have the tangent of theta. And both of these are ones that I remember the derivative for, but to figure out what an antiderivative or the indefinite integral is, for me personally, on both of these, I would use substitution. Now, how will we do this? On this problem, we may write a to the x as e to the ln a times x. Right? Now we see here, this is our inside function. So u is ln a times x, du is ln a dx. ln a here is a constant. Now, what do we have? Handed to us in our integral, we only have dx. So dx is 1 over ln a du. And this is my work I put in a box. Now let's convert to an integral of u. This becomes, well, this is e to the u, and then dx is here. It's 1 over ln a times du. right? Every single piece I converted to something of u. Here, this is e to the u. This part, dx, is here. It's 1 over ln times du. Now I integrate with respect to u, I get 1 over ln e to the u plus c. We go back to x. This is 1 over ln e to the ln times x plus c, which is, let me move this part over a little bit. E to the ln times x is just a to the x. So we get 1 over ln times a to the x plus c. And this is one that I personally remember. So you can put stars around it, something like this. This is for the indefinite integral for a to the x. And you notice, for instance, if you differentiate this, here's the constant, and the derivative of a to the x is a to the x times ln a. The ln a and this 1 over ln a multiply to 1, so we get exactly a to the x here. Okay, now this one, tangent. In order to see the substitution here, we really need to write this in terms of sines and cosines. So tangent, we know, is sine theta over cosine theta. Okay, and now where's our inside function? Well, if we take cosine theta, which is in the denominator, the derivative of cosine is negative sine. So we in fact do have a multiple of its derivative in our integrand. So here, u is cosine theta. du minus sine theta d theta. We have sine theta d theta, which is minus 1 times du. Okay. Now, this integral, sine over cosine, becomes, it's an integral 1 over u times minus 1 du, which is, I forgot my negative. Negative ln absolute value of u plus c, which is negative ln absolute value cosine theta plus c. So here is one way to write the indefinite integral for the tangent. And this was using substitution. But I will just add, me personally, I don't memorize an antiderivative for the tangent. It's not on my list that I memorize. I know, let's say I needed it, for example, I would just do a quick substitution, and then I would be able to calculate this when I needed it. This next example is a little bit more involved than the ones we have done so far, and that's because we want a specific antiderivative. We want a capital W such that, well, this is its derivative, but also it satisfies capital W of 1 equals pi. And so just as we did a few examples in the last video, this part we will use to solve for capital C. So we don't want as our final answer the indefinite integral here, which would be all antiderivatives and would have a plus C. We want a very specific antiderivative. Well, so let's get started. The first thing we want to do is integrate. So first, we integrate tan inverse of z over 1 plus z squared dz. And this one is very similar to one when we had ln x divided by x, because we see the tan inverse and we see its derivative. So the derivative of tan inverse of z is 1 over 1 plus z squared. And so we would take u to be tan inverse of z. du is 1 over 1 plus z squared times dz. And I have exactly du handed to me in my integral. So then I convert to an integral of u. This is just the integral of u du, which is u squared over 2 plus c, which is tan inverse of z squared over 2 plus c. Okay? That's just our first step. Like I mentioned, we have another step, which is here. So this is, all right, capital W of z, but then we want this. So capital W, so this is the end of the first. Now let's do the second. This is part 1, part 2. Okay. Well, capital W of 1 is tan inverse of 1 squared over 2 plus c. What's the tan inverse of 1? It says the tangent is 1 and sine and cosine are equal. Oh, yeah, tangent is 1 means sine and cosine are equal, and you're between minus pi over 2 and pi over 2. This angle is pi over 4, okay? So we get pi over 4 squared. This would be pi squared over 16 times 2 gives me this. Right? Now I want this to be equal to pi. So this should be, here, W of 1 is pi. So we want pi to be equal to pi squared over 32 plus c. Now we have the constant. It's pi minus pi squared over 32. This is my value of c. And so all that is left is to write down my final answer, which perhaps I will do at the bottom in black. Capital W of z equals, it's tan inverse z squared over 2, and then plus this constant, like this. So this is, here, this is the final answer. It's the specific antiderivative of this function that satisfies capital W of 1 is pi. Let's do 2 more examples. Both of them we will have to practice with the multiplier. And here is the first one. We have cosine of the square root of x divided by square root of x. Well, inside this cosine, we see square root x, and this is our very natural choice of u. When we differentiate du, well, we get 1 over 2 square root x times dx. Okay? Now, handed to us in our integral, we have just 1 over square root x dx. Which is, well, it's 2 du, right? If you multiply through this line by 2, we get exactly this line. Okay, so this part, the 1 over square root x dx is 2 du. Okay. Then, this integral is then, it's the integral, we have cosine u times, we have 2 du, then we integrate cosine positive sine, and finally we go back to the original variable, which is x. Here is our final answer. Now for the last example of the day, we have e raised to the 1 over t divided by 6t squared. Well, up inside the exponent of e, we have a function, 1 over t, and we have a multiple of its derivative in our integrand. And so u is 1 over t is a Great choice for you. When we differentiate 1 over t, we get minus 1 over t squared, then multiply by dt. So here's du. Now, if you look, I do not have exactly du. What's handed to me in my integral? Well, I have 1 over 6t squared dt. And this will be a multiple of du. Okay, so ask yourself, we go from minus 1 to positive 1 over 6. What are we multiplying by? Well, negative 1 over 6, right? This is our multiplier. And you can check. If you multiply this line by negative 1 over 6, we get exactly this line. And this is an important part. This is what I would always mess up when I first learned substitution. So it's good to check to make sure you have the right multiplier. Okay, so this part, the 1 over 6t squared dt is negative 1/6 du. Now let us continue with our integral. We have, it's an integral, we have e to the u times negative 1 over 6 du. Then we integrate, and finally we go back to t. This here is our final answer.